In this video, we will provide a generic definition of an optimization problem and define the solutions that can be found. As we have seen in the previous video, we can easily modify a maximization problem into a minimization problem. It is therefore valid to consider a generic representation involving a minimization problem. This is what we do in this course. We address mainly minimization problems. So an optimization problem, if you remember, is built based on three things: the decision variables, the objective function, and the constraints. So the decision variables, denoted by x, are represented by a real vector. So here we have n decision variables. So the vector of decision variables belongs to Rn. The objective function f is a function that maps Rn, so the set of decision variables, into R, which is basically the value of an indicator that we want to make as small as possible. We are dealing with a minimization problem. For the problem to make sense, we need at least one decision variable. Now we have seen in the various examples that the constraints of the problem can be represented by equations and inequations. So typically, the equation would be represented by a function h, such that h of x is equal to 0, and h here is a function of Rn, so which is the set of decision variables, and it maps into Rm, where m is the number of constraints, of equality constraints. And m in this case is greater or equal to 0. So if m is equal to 0, it means that the problem has 0 equality constraint. It has no equality constraint. In the same way, the function g that characterizes the inequality constraints maps the set of decision variable Rn into Rp, where P is the number of inequality constraints that must be non-negative. Sometimes it's convenient also to be more generic when we define the feasible set. So instead of characterizing the set of feasible solutions using equations and inequations, we could also say that x belongs to a subset of Rn, that I denote by capital X here, in such a way that x has some property. And a typical property that we will consider in various optimization problems is that when x is convex. Because when x is convex, we can derive some interesting properties of the optimization problem. So this definition is as generic as it can be. It's a minimization problem, but as we know, we can transform a maximization problem into a minimization problem. It can involve equations to describe the feasible set, inequations, and also characterize the set of feasible solutions using a convex set. So the feasible set is the set of values of the decision variables that verify all the constraints. So this is the set of x that verify the equality constraints, the inequality constraints, and x belongs to the convex set, capital X. So if we write it that way, the optimization problem becomes minimization of f of x subject to x belonging to set y. Okay. Now, what kind of solutions are we looking at? Well, the solution we would like to hope is called a global optimum. A global optimum is a point, and I will usually use a star to denote optimal points, such that the value of the function at x star is less or equal to the value of the function for any over x in the feasible set. So if I take a x here, the value of the function at x is higher than the value of the function of x star, and this is true for any x in the feasible set. So we will say that x star is a global minimum of our problem if the value of the objective function at x star is less or equal to the value of the objective function for any x which is feasible. Sometimes we can do better. We can find a strict global optimum. In this case, it means that the value of the objective function at x star is strictly better, so strictly smaller, than the value of the objective function for any x in the feasible set, which is the case in this example. So the only point that achieves the value of the optimum is the optimum itself. All other feasible points have a strictly higher value of the objective function. This is what we call a strict global optimum. So the definition is x star is a strict global minimum if f of x star is strictly less than f of x for all x belonging to y and x different from x star. Unfortunately, it's not always possible to find a global optimum. So some algorithm will be able to produce only something that we call a local optimum. What is a local optimum? A local optimum is a point x star which is better in the sense of the objective function than its neighbors. So more rigorously, it means that x star will be a local optimum if there exists a neighborhood, let's say this one, such that within the neighborhood, x star is the best point in terms of the objective function. So now if you consider this point here, let's call it x tilde. Well, if you notice, the value of the objective function at x tilde is better than the value of x star. So it shows that x star is not a global optimum. It's only a local optimum. Moreover, x tilde is not a local optimum. Indeed, you cannot find any interval such that x tilde will achieve the best value of the objective function in the interval. There is no such interval. Okay, so x star is a local optimum. X tilde is not a local optimum, but it's better in terms of the objective function than x star, which shows that x star is not a global optimum. So the formal definition of a local minimum is x star is a local minimum if there exists a neighborhood of size epsilon, strictly positive, such that the value of the objective function at x star is better than the value of the objective function for any feasible point which is inside the neighborhood of size epsilon. So like we did for the global optimum, we can define also the local optimum in a strict way. In any interval around x star is the best, but it's strictly the best. So all the other points in the interval have a strictly worse objective value of the objective function than x star. So the formal definition of a strict local minimum is that x star is a local minimum if there exists a neighborhood of size epsilon such that the value of the objective function at x star is strictly better than the value of the objective function for any feasible set within the neighborhood of size epsilon, any x which is actually not x star. So in this video, we have written a generic formulation of an optimization problem that involves equality constraints, inequality constraints, or even a convex set. And we have defined properly what types of optimal solution we can find. We introduced the concept of a global optimum and a local optimum. In the general case, only local optima will be identified by the algorithm. But there is one exception, is when the function and the constraint set are both convex. In this case, a local optimum will also be a global optimum.